Hello guys, welcome to this channel. My name is Roman Narvaez. I am a civil engineer with a specialization in structural engineering. I am sending this workshop from the city of Gothenburg here in Sweden. Right, today we are going to make a brief calculation about the Eiffel Tower. Principally the stresses that get this foundation. For this purpose, I have some points to go through. The first is that the picture you see on the screen is I used artificial intelligence to design this, and I put I show you the link later on. The background and geometry I take with the ChatGPT and Google, and later we are going to go through loads, analysis and calculations. Alright, here is the artificial intelligence I take for this midjourney.com. You can find there are more pictures that you can create depending on your creativity. ChatGPT is very useful for us to information as engineers, and as you told you before, the laws that I'm going to consider two laws. There is an approximation. It's not a very accurate. It's analysis and calculations. To go into this, I'm going to open my iPad here to show you the first part of this. I use the Procreate application. I made this presentation in this Procreate, so you see here the geometry of this tower. You find in this geometry that I take from the we will see. You can find this here in the Wikipedia, and you have this information to make this drawing or take care about the information of the levels. We have here, as you see here, 4 levels for calculations to make easier to get through these calculations, and we have in each of these heights some kind of area. I know that this is in Spanish, but the other that I found that was in French, so I am most quite familiar with Spanish. I couldn't find in English, but it's not a lot of Spanish, so maybe we can manage quite all right. Right, about the geometry, you find that the tower is around 324 meters with an antenna at the top of this tower. And you have L1, which is the first distance between the legs of the tower, and you have in the second floor or second level we have another area, and you have the third, and so on to the level number 4. About the loads that I am taking into account, the self weight. I take this load from the ChatGPT, and I'm going to take the wind, but I show you in what way. I must say that some background about Gustave Eiffel, which is he was a bridge engineer, very famous. At the time that he will get this assignment or project, he had another very famous like Gravite Viaduct. In France, we have the Statue of Liberty that are in New York, the Maria P. Bridge, and the Warsaw Railway Bridge. the idea of he was working a lot with bridges, and at that time bridges in steel. So as you see here, we have a section. The only that I made that was I take this to explain the Eiffel Tower and divide it in two to show you that this is the idea was that he got was that if you have a bridge, you can put together and you can make a tower. That was the main idea, and he did it. To get into the wind loads, I have a sheet here, and I show you the first considerations about that. The geometry, as I have been gone through that, we have here the cell weight. I translate this to kilonewtons, and the dimensions of the foundation. The dimensions of the foundation, of course, I can show you that I got from the ChatGPT here, and another master thesis I'll show you later. So this picture I take from the master thesis, and the information about the foundations, dimensions, depth, and total area are taken from this ChatGPT. So the other information that I use it here is of course the master thesis. Right, I found the master thesis of a mechanical engineer, 3D modeling of Eiffel Tower using the original drawings. I was looking about the original drawings, but I couldn't find. But in this thesis, I find many explanations about the geometry. But as I told you before, it will be a very briefly approximate calculation of loads. I would like to show you only the, for example, the elevation drawings stages that we were talking about. They're very complex, of course. To design all this steel. So here is the pictures about the foundation here. They took the dimensions of the masonry. And here is the picture. The pile on the masonry. So here is the deep that I say here is the deep of this foundation is 7 meters from the ground floor. All right, to the wind load, of course. The wind load, the information I take as well from the ChatGPT, and the pressure, the basic velocity pressure from the Eurocode. The nomenclature here for the Eurocode is the 1991-14, and wind pressure on the surface is calculated with the formula 5.1. So I need some kind of expression that I can use several times in different projects. So the peak velocity pressure are defined by the number 6. We will see if I have here the, okay, maybe where is this picture? Tower. Here's the velocity pressure. You see here the peak velocity pressure, the number 1, the equation here, and I can show you that you can find the Eurocode. Here we have the wind turbulence and other factors that you can find at that. So the main purpose of this is to find this factor, which is very useful, and you can replace and do by yourself and find the wind pressure and the sense that I have done here. Here is some factors that you use it. Of course, I will show you this in the error code. Here we have the error code. Here is the error code. So you have, for example, the peak of velocity pressure, some equations and the definitions of the exposure factor given in expression 49, which is the main goal to calculate the wind load. You have the wind turbulence, and in that way you can arrange these equations so you can find a final formula to take care of these calculations. You find this in a national annex as well. I know this is in Sweden, but Swedish, but I have pointed to the original in English, so you can find over there. Right, in that way, this exposure factor 44 is a function in the height of the building, and can put in the different heights that I show you in here, so I can find the pressure at different levels. I can plot or the curve of the wind pressure, the wind effect in different levels, and how I would do the body free diagram. Here is the tower. We are going to have three different levers, theta 1, theta 2, and theta 3. We are going to calculate R1, the reactions at the ground level, and the total moment. And how I get these forces at the different levels. You find here the different levels, and you have the length as well from the basis of each level. So in that way, I am using this trapezoidal formula to take care about the centroid of this geometrical figure here at the height h. But in my case, that's the area. For example, in the first part of here, the area, I take a percent of this. So if we get back to this picture, we see at the first area here, we have an open space here, which I made approximation around that the influence of the wind and the horizontal or lateral direction, it would be only 30%. So you find 30% of this area, it would be that equal. Deliver about the first theta 1, of course. Show you here theta 1, the first lever here for the moment, and in that way I multiplied the area by the wind factor, the height and the pressure here. I get the 62,070.49 kilonewtons per meter. The same procedure I made for the area number 2. I take only the 30%, a little higher. So the second here, and the area for that. In the same way that like the first, only that I have the lever plus H1, and the lever would be 84.11. I take the moment for this force, the second moment. I made for the third level as well. Here is for the third level, and there is the force over there. Here I take 30% as well. So I get the lever 185.92 meters, and the moment of this number 3 is a big one. We have a 1,195,212.06 kilonewtons per meters. So the total moment is the sum of the 3 moments for partial forces. And now I need to apply the Eurocode. And the Eurocode told us that, for example, if you are going to use a partial safety factors for ultimate limit states. So I use this partial factors, 135 for the subweight and 1.50 for the variable load. In this way, this is the wind. You can find this kind of things in the structural elements design manual working with error codes. Yes, and you get for the total moment 2085.29 meganewtons per meters. I apply the error code to the subweight. Here you have 2 things to think about: is the steel, the force of the steel, the vertical force, but you have the foundation as well. The foundation I take for the first, here you had with ChatGPT the area of the foundation and the thick of the foundation, or the depth of the foundation. As you can see, a density of 24 kilonewtons per cubic meters. Sorry, you get that information, and of course you get 70,200.0 kilonewtons. Here I'm looking here that maybe this is a all sorry, a moment, I'm going to look something here. Area for we see where I have this information right now. In foundations, of course, I can show you. I'm going to apply this kind of Navier's formula for foundations, and here is 3 cases when the eccentricity of the loads and moments are less than the whole length of the foundation. And you have 2 cases here. Of course, I'm making these assumptions. You get the first equation here, and you have 3 forms of the soil is producing a pressure on the ground. So that's where you see here. So I need the dimension of the foundation, and the dimension for the foundation you take from this picture here. So L1, L5. In my case, L5. I haven't put here L5, but L5 here is the 74.24 meters. So in that way, you get an area, a total area only for the one leg. You have in the case that you have 2. If you make this for the first, you have 2 legs, but you must divide by 2, and you get an eccentricity when you divide the total moment to the vertical load of 29.70 meters. and this is bigger than the total length of the foundation divided by 6. In that case, you use the formula here, which is that one. Only the pressure of the soil is like QA1. So I put the values here and get a pressure on the ground 879.27 kilopascals. So this is an approximation, but you see that the cell weight and the wind loads are influencing this structure and a big pressure on the ground. Of course, you can make more precisely approximations and refine this calculation to the ground. That's all for today. This kind of calculation I can show you. I have done another for a big building here in Gothenburg, which is Carla Tunnel. Maybe I would like to show you a little about that. Carla Tunnel. Gothenburg. So I have done another calculation, another presentation, but I am not ready right now with that, and we can compare later on the Carla Tunnel here in Gothenburg with Eiffel Tower in Paris. I hope that you get some knowledge about that and some ways to improve your understanding about structural engineering. Okay guys, see you later. Have a good time. Bye.